A JWST MIRI survey.
Okay, hi everyone. Okay, well, thanks for hanging in there to the end of the day. This talk is really a preview of my talk next year because we just got our data, but I wanted to advertise my survey. This is my own survey. I'm the PI, and these are all the team members who have been working on it as well. So MEGA is designed to be a wide field, a JWST wide field survey. It was observed in cycle 2 over 67 hours. Like I said, we just got our data. It was observed at the very end of March, so we've only got a preliminary reduction right now. But the point was to do 30 pointings covering existing near-cam and near-spec observations in this year's field. And so the green things up there are the Sears pointings. Only a mere four of those had longer wavelength MIRI data. And so with MEGA, which is shown in yellow, and completing the shorter wavelength Sears MIRI data, we now have 30 pointings that have data all the way out to 21 microns. We can compare to other MIRI surveys, and MEGA is the widest area survey in more than 3 filters. And we reach about a similar depth to SMILES, which is the other big MIRI survey, which has observed in multiple filters. So this was our design. We did four MIRI filters. And the reason that we picked these 4 filters was really because I'm focused on cosmic noon science. So don't kick me out of your conference, please. And so the idea was that we wanted to be able to try to reach similar depths, get the same galaxies in each of the 4 fields. The plot here shows the red dashed line is the Spitzer luminosity limit from their deep surveys. And then the dashed lines down here are predicted luminosity limits from our design. And by combining in a field where we have lots of near-cam and ACS and with C3, we're hoping to be able to do this kind of robust spectral energy distribution fitting. So we have 2 main science goals. The first thing that we're trying to understand is the universe, is mass assembly truly coeval? Right, so prior to JWST, there is this idea that cosmic noon is when the star formation rate density peaks and when the black hole accretion rate density peaks. This plot over here is from our work in Sears, and it shows that from just based on 4 pointings, the 4 MIRI pointings, right? So we're talking about 400 galaxies. You're able to identify basically a handful of AGN, and shows that AGN growth actually might be there might be more AGN growth at redshift greater than 3 than previously thought. So this is something we really want to pin down. The other thing that we want to pin down with MIRI is you all have been showing these really lovely near-cam morphologies. We want to do the same thing with MIRI and look at the dust-obscured star formation and how that shapes the evolution of galaxies. Okay, so like I said, we have our data. That's it. It doesn't look like anything. There's way too many photons in here. I have to figure out how to show this better. So we've processed it, and here I have a zoom in. So there we go. So that's a multicolor MIRI image. So none of this is near-cam. This is all MIRI. And so with MIRI, we're able to see, starting to see the shapes of galaxies, of very distinct galaxies. And I'll show you some more impressive images in a little bit. So based on previous work with Sears and those 4 Sears pointings, I had written a paper investigating what were the strengths of MIRI compared to Spitzer. And so here we're just looking at the luminosity and redshift distribution. The gray points are Spitzer 24 microns, and then the orange points are MIRI at 18 microns. And what we found initially when we had done these predictions for what MIRI was going to see, I kind of thought they would see more high redshift galaxies, but what we found was that JWST's real strength is this cosmic noon epoch, because now we can really push very far down the luminosity function in a way that we weren't able to do before. And so we can study, we can find obscured AGN, we can look for obscured star formation, and we can look at unobscured star formation all in these lower luminosity galaxies. But what we weren't able to do with the original Sears pointing is find high redshift galaxies. So we really couldn't say anything about them. So is that a product of there being just a really, really small area? Does MEGA improve on this? The answer is that yes, it does. So from our preliminary reduction, we have about 4,000 galaxies detected in 770. And I'm showing the distribution of their redshift versus the number of sources. So again, we get those peaks at redshifts of 1 and 2. This is kind of due to pH features falling in the filters. And we did pretty well meeting our goal of trying to get the same types of galaxies in all 3 filters. So 64% of our galaxies have detections in 3 bands. Those are the blue. So again, we're not biased with redshift. They're pretty evenly distributed. 51% of our galaxies have detections in all 4 bands. And so now we can look at that luminosity and redshift distribution again. And this is now 21 microns, which is my favorite band, because I really want to probe the dust as long as possible. And now we are seeing many, many more high redshift galaxies. So that population's not missing anymore. You just need to do a large area MIRI survey to get at it. Okay, morphologies. So we did a lot of our setup for what we were going to do with morphologies. We tested with primer, since we were waiting for access to our data. So again, many of you in the room are probably in primer. It's a survey looking at Cosmos and UDS. The limitation to primer is that the 18 micron data is kind of shallow and it doesn't have anything but 7.7 and 18 micron data. That's just another view of primer galaxies. So we've heard some talks about morphology. So we were interested in doing visual morphologies with primer data. We're really interested in doing that with MEGA as well. We're also doing parametric fitting and non-parametric fitting. But visual morphologies are very powerful. And so we created a citizen science website. Right now it's in beta testing, so we only have 300 galaxies up there, but we're going to put all of our primer galaxies and all of our MEGA galaxies. So there will be like 10,000 up there. And we are asking people to classify if they're disk or spheroid, you know, yada, yada. If this is something that you are interested or you teach a class you're interested in using, that's our QR code. Everyone can get involved and help us classify galaxies. Okay, so our results just from 300 galaxies with primer are basically the same results that Mark already showed. We classified, you know, the number of disks and spheres as a function of redshift, and similarly, different methodology from what Mark was doing, different field, but same results, right? Which is that we see these disks and these spheroids at redshifts of 1 to 2, and then the disks in the spheroid fraction drops down at redshifts of 3 to 4 to 5, and you start to see the irregular galaxies. Okay, so that's primer, but what we want to do with MEGA, what we will be doing, is doing the same sort of analysis, but now classifying the longer wavelength data as well. Again, the resolution here isn't as pretty as on my screen, but this is an example of one of our galaxies at 7.7 microns and at 15 microns. And what you guys can't see as well as I can is that there's spiral arms visible in the 15 micron image. There's another example of that one. That one's much clearer, where we have these beautiful spiral arms visible at longer wavelengths. And in fact, we can see spiral arms all the way out to 21 microns. So this is something, of course, that we'd never be able to do with the previous generation of infrared telescopes. And so now we will be able to trace these morphologies as they evolve in the dust as well as in the stars. All right, our next major goal was AGN and star formation. And again, I'm going to talk about Sears first before talking about MEGA. So this was my paper on the 4 Sears MIRI pointings. And what I found, and I'll show you in a minute, was that it was actually pretty hard to identify AGN. Out of 400 galaxies, we only identified through spectral energy distribution about 25 to 30, and that was through like 2 different spectral energy distribution methods. But what I was able to do with MIRI is really explore what that lower luminosity population at redshifts of 1 to 2 looks like, which was, again, something we haven't been able to do before. So I made composite spectral energy distributions of these galaxies based on their infrared luminosities. And what we find is that the higher luminosity bins, the infrared luminosity shape, the shape of these galaxies is all very, very similar. This is what was known from Spitzer and from Herschel. But now we get to go down to these lower luminosity bins, and we find that the diversity of shapes is quite variable, right? So all bright galaxies are alike. Each faint galaxy is faint in its own way. So there's just a lot of scatter that we weren't able to see before. And so we can take these spectral energy distributions and can put them on the same plot, right? And so now we can really compare the difference in shape. And so the first thing that we found is that things are not faint in the mid-infrared because the PAH strength is changing. We were able to measure the PAH fraction, and when you consider the PAH fraction to the rest of the dust, the PAH fraction is basically the same for all of these galaxies, right? So the PAH is, so the same amount of dust emission is being emitted in the PAHs. What does change is that ratio of optical to infrared emission. And so MIRI detected galaxies at redshifts of 1 to 2 still are dominated by unobscured star formation when you were talking about these fainter galaxies, right? Which was a little bit unexpected because for more luminous galaxies, you see the amount of dust that they have increases, and dusty galaxies at high redshift, sorry, it's not high redshift anymore, at cosmic noon are significantly different than ULIRGs, for example, in the local universe. And so I was naively expecting that the ratio of mid-infrared to optical for these higher redshift galaxies would be different than what you would see in galaxies locally, but it's not. Lower luminosity galaxies, their spectral energy distributions look the same from redshift of 0 out to redshift of 2. Okay, and then what about those pesky AGN? Again, I didn't find very many. It's actually kind of funny. I'll tell you guys a funny story about how you sell something. So I wrote my paper at the same time that Guang Yang wrote his paper, and he used a different method to find AGN than I used. And we both found the same number of AGN, but I, in my story, framed it as there's not as many as I expected, and he in his paper framed it as there's a lot more than I expected. And so people thought we had conflicting results, but we didn't. We identified the same ones. Okay, so AGN were unfortunately less numerous than I was hoping. I was hoping that we would be able to identify a lot more AGN once we had spectral energy distribution, more spectral energy distribution coverage, but we didn't. They turn out to be about 10% of the population, irregardless of infrared luminosity. Okay, so what about mega? So now we've expanded this. So now we have 30 pointings of data. So I'm going to show you very, very preliminary data. This is our mega data. So I'm going to walk you through what is on here. So on the x-axis is 15 microns over 7.7 microns, and on the y-axis is 7.7 microns over 3.56 microns. Okay, and then these are our mega galaxies. The different redshift lines correspond to my templates. This is one of the ones from my paper that was like one of those mid-IR weak ones. This is a dusty star-forming galaxy, and then the red one is just a power law AGN. So I have found in all my work looking at color spaces that when separating AGN and from low metallicity galaxies, it really helps to have an anchor point on each axis. So that's what the 770 is doing here. And so the boxed region then shows where the power law sources are. Now, one of the other things that we found is now that we have all these very closely spaced filters, is that you can actually mimic a power law from PAH features alone if you don't know like precisely what redshift you're at. So I had an additional requirement to see which ones are really power laws by also requiring your 10 micron to be greater than your 770 micron to be greater than your 444. Okay, and so again, you can see some of the sources that are power law in that requirement. These are the dark shaded sources, aren't power laws in this requirement. It happens to do with if you just happen to be relying on a feature, you can mimic a power law, but you do not really have one. So I'm calling everything AGN that lies in the box and meets that additional power law requirement. Of our survey, and so then I'm going to show you even more preliminary data. So this is very preliminary, like I literally made this in my hotel room last night. Okay, so yeah, I know there's no error bars, but this is our fraction of our sample that are AGN candidates, so the ones that lie here, compared to everything else, as a function of redshift. And so there's a couple of things that I want to point out with this, and that is that, again, it's only about 5 to 10% of the sample. Even with this expanded sample, it's only about 5 to 10% of the sample that are detectable as power law AGNs in this method. Yes, it seems to be increasing as we move out to high redshift. However, that might not be physical because a couple things could be happening here. Number one, our luminosity limits as we move out to higher redshift are higher. We can't detect as much faint stuff. Well, AGN are preferentially more luminous, so this could just be a selection effect. It could also be, the reason that we need another telescope after James Webb, is that we're not actually probing the dust anymore once we move out here. So power law selection might not be selecting AGN at all. Okay, so what are we doing to improve on this? So like I said, this is about all we can do with SED fitting is going to give us very similar answers to color selection because they're based on similar ideas. So I have a grad student who's writing his thesis. He has developed this code called AGN Boost. It is a gradient boosting machine learning method. We're hoping to have the paper out this fall. And basically, this code does what I couldn't do, which is it uses just MIRI data to find AGN. So we've trained this on millions of mock observations with Segale. We set aside about 10% for testing, and then millions for training from redshifts up to 1 up to redshift 8, and with varying AGN fractions. And then we just put in all possible MIRI color combinations and used a gradient boosting algorithm, and this is how it performs. It can actually predict a redshift really well up to redshift of 4. It can't do it past that. The reason, again, is the dust features. Right, below redshift 4, you have these very clear MIRI dust features, so you can get mid-infrared redshift. And then it predicts the AGN fraction really well as well. So we are hoping that this kind of machine learning tool should be viewed as complementary to other AGN selection methods. But the benefit to having a machine learning tool as opposed to something like Segale is that, I don't know if you guys have used Segale, there's a pretty steep learning curve, and also it's very computationally expensive. And so we wanted something that was just really fast to do this kind of work. So that's all just an advertisement of my students' work. So like I said, in conclusion, MEGA is the largest area MIRI survey in 3 bands. Our reductions are ongoing, and our main science goals are to study the distribution of obscured star formation at cosmic noon. And indeed, looking at our images, we already do see spiral structure, and our cosmic noon galaxies are just dominated, and then to constrain black hole growth through accretion. And so far, about 10% of our population. But now we have, because we have 4,000 galaxies, right, we have hundreds of AGN to look at, as opposed to just like a handful. So stay tuned. All right, thank you.
Awesome, thanks for that, Allison. Plenty of time for questions.
you have a sense yet of what fraction of these galaxies at cosmic noon are disk dominated at some luminosity or whatever?
Yeah, what we were finding was about 50%.
50%. Did you show that? I just missed it.
It
Thanks.
was briefly on a slide.
Thank you.
It's okay.
At roughly what stellar mass is it 50%?
Oh, I haven't looked at it as a function of stellar mass. This was my summer RAU project for a student, so that's a good idea, though. We will do that.
More questions?
I think David.
Given the resolution that you're able to achieve, can you in fact separate the central to the outer regions and compare the two? Because I think that if AGNs were to have any component, you might see it better where the signal noise is higher in the middle, and you get a different sense of the gradients of properties that might give you a hint of the AGN, even if without the direct signature.
Yeah, exactly. That's a really great question, and this is something that we want to do. I actually tried to do it with HST this morning, years ago. But the idea is that can you separate, since you have higher resolution, can you separate the center and do photometry on the center and then photometry on the outskirts? Yes. So we are exploring doing this through two different ways. We have both Galfit will do this kind of thing for you, and then we are also using a machine learning code developed at Yale by Arisha Ghosh called GAMPIN that will pull out a point source as well, but hopefully it will work.
I haven't thought about this before, but I was just thinking about how you could see more infrared selected AGN at high redshift because of selection biases, because it's basically the ratio of the AGN light to the galaxy light. You've got brighter AGN, lower mass galaxy. Like, it totally makes sense. But maybe there's a way you could model that, and then you could compare your observations to see how much of that's just due to the evolution of the selection bias.
Right. So, okay, I will pontificate on this for a minute. So I had written a paper back in 2017. Don't go read this paper because it was wrong. But that's what I did. So this is why when I wrote this paper with Sears data, I said, oh, there's not that many AGN. It's because when I had done this back in 2017, I had modeled putting an AGN spectrum on top of the galaxy spectrum, and as you lowered the galaxy mass, assuming the AGN accretes at the same rate, how many AGN would you see? And it's a lot more. And so I don't know the answer to your question, because as you move down to lower redshift, or not lower redshift, lower mass galaxies, the AGN accretes very differently, and it becomes not as luminous. And so I actually think it's harder to find AGN in lower mass galaxies.
Awesome. Let's thank Allison again.